the physiology of the heart muscle cell or myocyte. Heart muscle cells or myocytes have a unique feature not shared by other cells in the body. They have the ability to respond to an electrical signal and generate an action potential. This causes each muscle to contract as a result. What's unique about them is that they are somewhat leaky, so they don't keep a normal electrical charge steady at all times. They do not necessarily have to wait until they get a signal from elsewhere in order to contract. And because some electrolytes leak through the cell membrane, they can cause their own action potential without outside influence. This is called autorhythmicity. Before we get into that, let's look at what a resting potential looks like and how it is created. The resting potential of a cell is the electrical charge difference between its inside and outside. Most of this charge difference comes because of the different amounts of charged ions due to the cell's sodium-potassium ATPase pump that is continually pumping sodium out of the cell and potassium in. Because it sends out 3 sodium ions for every 2 potassium ions pumped in, the cell is steadily charged more negatively on the inside, called the resting potential. It looks like this: sodium, potassium, pump 3 Na plus out, 2 Kepos in. ATP. ADP. P. Active translocation needs ATP to pump. 3 sodium ions are pumped out of the cell. 2 potassium ions are pumped into the cell. An action potential for any cell involves a change in the charge differential or voltage across the membrane. Usually it happens when sodium enters the cell, causing a more positive charge inside, called phase 0. Let's look at how this works. Cardiac muscle action potential. Plateau, maintained depolarization due to K inflow when voltage-gated slow K channels open and K outflow when some K channels open. Repolarization due to closure of K channels and Kdeg outflow when additional voltage-gated K channels open. Membrane potential, MV. Rapid depolarization due to Na inflow when voltage-gated fast Na channels open. 60, 80, 100, L, 0.3 sec. The normal heart muscle cell has a resting potential of about 90 mVAS across the membrane, being more negative on the inside. This is called phase 4 for some weird reason. Sodium enters the cell in phase 1. This starts the process known as depolarization. The sodium ions add a positive charge so that the cell is temporarily positively charged. The charge returning to its resting state is called repolarization. This whole process of depolarization and repolarization is called the action potential. There are several different potassium channels in the cell membrane. In phase 4, a series of leaky potassium and calcium channels allows the membrane potential to change slightly. This takes it to a 70 mV state. This inherent leakiness is what triggers the heart muscle cell to spontaneously fire and contract without outside influence. Then in phase 2, sodium channels open and sodium floods in. The charge in the cell becomes positive at about plus 50 pounds/mV, after which the sodium channels close quickly. Phase 1 then starts, as potassium channels open up to allow potassium to actively leave the cell, driving down the electrical gradient. Phase 2 is when the charge differential plateaus, staying the same because calcium levels become high in the cell to keep the charge positive for a period of time. After phase 2 ends, the calcium channels close and calcium is pumped into the cell's sarcoplasmic reticulum. At the same time, potassium leaves the cell in phase 3. This rapidly depolarizes the cell, essentially taking it from its plus 50 mV state back to its former 90. Of course, it is during this entire time that the cardiac muscle cell contracts.